In outbreaks of disease, it's useful to have a mathematical model of the diseases in order to effectively combat it. Since we're in the midst of a pandemic and are currently discussing modeling and numerical analysis, this is an ideal time to discuss mathematical models that can help us in controlling the spread of disease. This falls under an area of medicine known as epidemiology. So, in case you're interested, epidemiology is the study of the distribution and determinants of health-related states or events in specific populations and the application of the study to control health problems. That's from the CDC. It's also defined as the study of the distribution and determinants of health-related states or events, including disease, and the application of the study to the control of disease and/or other health problems. Various methods can be used to carry out epidemiological investigations, surveillance, and descriptive studies that can be used to study a distribution. Analytical studies are used to study determinants. Since I know that you care, here's the definition of epidemiology from your frequently drunk but occasionally correct friend Wikipedia. That says epidemiology is the study of the distribution and patterns of health-related events, health characteristics, and their causes or influences in well-defined populations. So these all match up pretty well with one another. So some more definitions, and these are important. An epidemic is a fast-spreading disease, an outbreak of a disease that spreads more quickly and more extensively among a group of people than would be normally expected. And a pandemic is an outbreak of disease prevalent over a whole country or the entire world. So here the scope and scale are the important items, but these two words often get used interchangeably. So let's take a little bit of a look at the history of epidemiology. And we can start all the way back around 400 BC with Hippocrates. And he's the one for whom the Hippocratic Oath is named. And he hypothesized that disease may be associated with the physical environment. And that was due to him looking at seasonal variation in illness. The next thing that came about was in the 14th and 15th century, the idea of quarantine came about as a way to combat the bubonic plague. And the word quarantine originates from quarantina, the Venetian language form meaning 40 days. And since bubonic plague had an incubation period of 37 days, this actually worked quite well. Keeping the ships from landing for 40 days worked quite well in keeping Venice relatively free from the plague. You may not recognize the photo that I've included here of the Kalapapa leper colony way back in 1905. People were removed from their families and quarantined here to live until the disease claimed their lives. There are quite a few good versions of the story, and this continues to touch and affect people in Hawaii. So definitely take a look at that if you have time. Moving on to the 17th century, the 1600s, John Grant published Nature and Political Observations Made Upon Bills of Mortality. That's pretty long-winded, but basically he was the first to employ quantitative methods in describing population vital statistics. And Malthus did population modeling, and basically the short-term growth of population is exponential, but unfortunately our food supply is not. And growing populations of all different types of species tend to outstrip their food supply, and this provides a natural check on population growth. Connections between demographics and epidemiology were certainly shown by Malthus. Moving on to the 19th century, we can take a look at John Snow, and I'll have a companion presentation on him. And he was the one who solved the fact that cholera was waterborne, and basically birthed the modern field of epidemiology. His investigation of the 1854 cholera outbreak was certainly a game changer and helped lay the groundwork for the idea of germ theory. He was also the constructor of the ghost map, which was a Verneuil diagram that allowed him to see that the cholera was actually emanating from a particular well in the Soho district. And William Farr was a contemporary of Snow's, and he compared the mortality of inpatients of asylums in England. And he looked at the more modern Hanwell Asylum and compared it to the older one. Hanwell had about a 12% mortality, which is pretty high. But when you consider the others had 27%, that was as high as the mortality rate of British soldiers who were fighting in Africa at the time. That's pretty scary if you're choosing that as a place to go get better. So this brings us to the 20th century, and the common model in use, or one that is fairly common along with its variants, is the SIR model. And it's a compartmental model of disease that originated sometime around the outbreak of the Spanish flu, which was about 1918 or so. And in a compartmental model, populations are put into compartments. There's S for susceptible, I for infected, and R for recovered. Using ordinary deterministic differential equations, we can show the rate of change of these various populations. And we're going to do a little bit of a walkthrough from a case study from the Mathematical Association of America that was authored by David Smith and Lang Moore, and I'll try to link to that in the Lima site. And as I mentioned, there are numerous variations on the SIR model. For example, the SIRD model, which puts people into susceptible, infected, recovered, and deceased, whereas SIR just moves the dead into the recovered pool. There are also models for childhood diseases that account for immunity inherited from the mother for a particular amount of time. In terms of differential equations, I found a couple discrete versions of the model that will let us explore without getting too much into the 300 level math classes. For those of you who are just arriving from CS 151, you can thank me for that one later. So moving on to the case study. The case study in the Mathematical Association of America looks at the Hong Kong flu outbreak during the 1968 and 1969 years in New York City. And the data displayed in the following table is the excess pneumonia influenza-related deaths, basically the number of deaths in excess of the average number to be expected from other sources at the time. And the graph displays the same data. So you can see kind of in weeks 5 through 8 that this particular flu peaked. Relatively few flu sufferers die from the disease or its complications, even without a vaccine, and there wasn't one for the Hong Kong flu. However, we can reasonably assume that the number of excess deaths in a week was proportional to the number of new cases of the flu in some earlier week. Say 3 weeks earlier, it takes you 3 weeks to go from infected to passing away. Thus, the figures in the table represent proportionally the rise and subsequent decline in the number of new cases of the Hong Kong flu. We'll model the spread of such a disease so we can predict what might happen with epidemics that take place in the future. And certainly now is the future. So in the SIR model, there are 3 populations. At any time, the fixed total population can be divided into 3 distinct groups. I of t, the number of people who are infected, R of t, the number of people who have recovered, and S of t, the number of people who are still susceptible. We can use small s of t, small I of t, and small r of t to denote the fraction of the total population in each category, and that won't change because we're dividing by n. In this case, N is 7,900,000, which was about the population of New York City in the late 1960s. T is our time-dependent variable, and our independent variable, and the rest of them are dependent variables upon time. And again, it may seem more natural to work with the population counts, but some of our calculations will be simpler if we use the fractions instead. And so the 2 sets of dependent variables are proportional to each other. So either set will give us the same information about the progress of the epidemic. So moving on to some assumptions in this model, no one gets added to the susceptible group. We ignore births and immigration into the city. The change in the susceptible population, or the number who are already susceptible, the number of individuals already infected, and the amount of contact between the susceptible and infected individuals. So each infected person has B contacts per day, although only B times S T are susceptible with susceptible individuals. So on average, you get B times S of T new infections per day. And we also have a fraction K of the infected group that will recover during a given day. So, for example, if the average duration of the infection is 3 days, then on average, about 1/3 of the currently infected population recovers each day. Strictly speaking, what we mean by infected is really infectious. That is capable of spreading the disease to other people from the susceptible pool. A recovered person can still feel pretty miserable, and they might even die later from pneumonia. Hopefully not, but they definitely stay in the recovered population in the SIR. So let's look at the equations. The susceptible population will obviously decrease as they're exposed to the infected based on the contacts that they have with those individuals who are infected, and those are the first two equations. The recovered equations dependent on the number infected and the recovery time. And since we don't have changes in the total population, the equation for the infected individuals is based upon the other two, namely the susceptible and recovered. And so we can actually go about determining the equation for the infected. We can solve these using Euler's method, which I'm guessing gets covered in Math 300, but we'll skip on some of the details of the calculus. And if we look at our case study with Hong Kong flu, there were about 7.9 million people living in New York City at the time and about 10 infected people at the outset. So the susceptible population was equal to about 1. The infected was equal to 1.27 times 10 to the minus 6 as a proportion of the population. Again, only 10. And nobody had really recovered yet, because we're just starting out. So you can't recover from a flu that you haven't had at that point. We set K equal to 1/3 since the recovery time was about 3 days, and set B equal to 1/2 to model an infected contact for each infected person every 2 days. The results look like the graph pictured here below. And of course, tinkering with the parameters does change things, and you'll have a chance to do that in one of the accompanying assignments. The article goes on to discuss how to use Euler's method to solve these differential equations and to make a model that you can implement quite easily in a third-generation language. It also explains how herd immunity works and how to calculate various vaccine efficacies. Now, epidemiology is a great tool, but you need to be cautious, particularly with these models. And some of the models that have had trouble, the first one I'll introduce is body mass index. And this was invented by the Belgian mathematician Adolphe Quetelet in the 19th century, and it was part of something known as social physics. Now, he wanted a quick measurement for the government to look at the overall population. And his method for coming up with this was not scientifically accurate and pretty much on par with an area known as phrenology. I'll let you look that one up and why it's a pseudoscience. Other techniques are much better, but this little hack happens to be cheap and happens to characterize the overall population. Problem is that it doesn't do well with individuals. Michael Jordan, during his prime with the Chicago Bulls, was overweight, and this gets criticized from both the left and the right. NPR had a story that was highly critical of the body mass index as a measure of health, as did Reason magazine. One of those is fairly far to the left of the political spectrum. One is fairly far to the right on the political spectrum. And boy, if Michael Jordan is overweight, I am in trouble. So if you want to calculate the body mass index, you divide the weight in pounds by the height in inches squared and multiply by a conversion factor of 703. You look up the ratio in a chart. If you're below 18.5, you're underweight. 18.5 to 24.9, normal. 25.0 to 29.9, you're overweight. And 30 and above, you are obese. Now, in 1998, the National Institute of Health lowered the ratio. So, what would happen if you lower the ratio? Well, more people actually became obese. They dropped the weight by about 10 pounds for each category. So, you moved more people from normal to overweight and more people from overweight to obese, more people from underweight into normal. And so you ended up with a lot more overweight and obese people simply by changing the ratios. Nothing the population itself did. So this resulted in increased funding for the obesity epidemic, which it did get them a lot more money, but probably wasn't the most scientific thing to do. And another one that generated some real problems was a Lancet survey controversy. And these were two peer-reviewed studies on the Iraq War deaths that took place in 2004 to 2006. They counted 654,965 deaths, whereas other studies placed the number of deaths from this war at around 100,000. Still absolutely horrible, but they came up with 6 times the number of deaths. Now, this was primarily discredited by right-wing news media, but also by the Iraqi government and other researchers in the area of epidemiology. So it had a couple problems. One was cluster analysis, which divides the area into a number of randomly selected, approximately equally populated regions. You choose a random point in each region and interview a fixed number of households. There's also the Main Street bias in that they only interviewed households on accessible cross streets, and they didn't always get death certificates. So numerous people ended up being counted more than once in terms of their deaths. And of course, many people on the far right will point out George Soros, although I don't think that had anything to do with it. The study was never totally scientifically refuted, but it still causes some credibility problems in the field of epidemiology based upon the methods used in counting individuals more than once in the proverbial Deadpool. Anyway, thanks so much for listening, and I hope you enjoyed taking this little trip down the subject of epidemiology. If you're interested in more, I can point you in the direction of resources, and it's a really cool field to study. So